Okay, good morning, bright and early. So let's look at problem 113 from worksheet 8 on doing titration curves. It says draw a curve for a series of solutions of HF. Plot the hydronium ion concentration total on the vertical or the y-axis and the total concentration of HF, the concentrations of both the ionized and non-ionized HF molecules on the horizontal axis or the x-axis. Let the total concentration of HF vary from 1 times 10 to the negative 10th to 1 times 10 to the negative 2. So you know what that axis has to vary over. And we're going to start by thinking about what we need to know. So when we take HF and we put that in water, we are going to get hydronium ions and we're going to get F minus ions. The Ka for this reaction is 3.5 times 10 to the negative 4th. So this is a pretty weak acid. So what does the Ka statement look like? Ka would equal the concentration of H3O plus times concentration of F minus divided by the concentration of HF. So I know that I'm going to have to concern myself with the concentration of the autoionization of water because this Ka is pretty small and we're going from some very small concentrations of HF to a fairly high concentration. So at some points on this, you're going to have to use the quadratic formula. So the self-ionization of water will be an issue. So we are going to use, here's the R part of it. We're going to have to do rice. And let's start with our weakest concentration of HF, which would be 1 times 10 to the negative 7th. This is going to be, because of the self-ionization of water, 1 times 10 to the negative 7th. This will be 0. So can we figure out which way this reaction has to shift? Well, of course we can, because if this is 0, we have to shift and make more products. So I'm going to lose X here, I'm going to gain X here, and I'm going to gain X here. So this is going to be 1 times 10 to the negative 7th minus X, 1 times 10 to the minus 7th plus X, and X. So now you're going to put these three values in here, and it's going to equal this. So 3.5 times 10 to the negative 4th is going to equal 1 times 10 to the negative 7th plus X times X divided by 1 times 10 to the minus 7th minus X. So I think you can work out the quadratic. I will give you what the quadratic is once we multiply all this out, and we get x squared plus 3.501 x times 10 to the negative 4th x minus 3.5 times 10 to the negative 11th equals 0. So in your calculator, you should be able to figure out this quadratic. I've already done that part, and I get that x is equal to, you get two values, only one of them will make any physical sense. One's positive and one's negative, and we want the positive value. So x equals that. We're not quite done. That is the value of x. That tells me the F minus ions, but it does not directly tell me the H3O ions. I have to add this to the 1 times 10 to the negative 7th. And if you do that in your calculator, then you get that, let's see, the value is 1.999 times 10 to the negative 7th molar. So your first point, this is your hydronium ion concentration. And we know that the HF concentration was 1 times 10 to the negative 7th molar. So now you have your first point. You're going to continue this idea at various concentrations, and you're still going to have to worry about the quadratic for at least a couple more concentrations. I would use the quadratic throughout. So I'm going to stop here because that'll give you a chance to go on and try and do the rest of these plots or points. I will give you an idea of what the sketch should look like. And so here's the plot. Again, we already talked, this is going to be the concentration of HF. So that would be these numbers that you select. This is going to be the concentration of hydronium ions on this plot. And we're going to start with 1 times 10 to the negative 7th as our lowest number. And I'm sorry, I've got that on the wrong axis. I'm sorry. We have no idea what these values are going to be, but they did tell us what values we had to use here. And they told us to use 1 times 10 to the negative 10th up to 1 times 10 to the negative 2. And I would do several positions along there. And we did times 10 to the negative 7th, which is somewhere around here. And we're going to have, we know below that it's going to be just the concentration of hydronium ions in water. So this would be 1 times 10 to the negative 7th. And so it's going to look something like that. Now, depending on your scale, etc., it would look different, but this is a general idea of what you want to see. That should be enough to get you through the rest of this calculation. And there is a second one that you should do, so that should give you plenty to work on. Have a great day.